Have you ever stopped to think about how scientists can find one single drop of an impurity in a huge vat of medicine? Or get this, how they can spot one pollutant molecule in a million gallons of water? Well, it all comes down to this amazing art of unscrambling the scrambled. It's a scientific technique that, believe it or not, quietly runs our modern world. It's all about taking a super complex mixture and pulling it apart piece by precise piece. I mean, really think about it. When things are all mixed up, sometimes down to the molecular level, how in the world do you pull out just one little thing? It sounds almost impossible, right? It's a massive challenge for sure, but it's one that science actually solved over a century ago with this just remarkably clever technique. In just about every field you can imagine, we're talking pharmaceuticals, environmental testing, you name it, scientists are always facing this problem of separating mixtures. And to do that, they have to rely on this one fundamental, super powerful technique. And that technique is called chromatography. Now, its name actually gives us this beautiful clue about where it came from. It's from the Greek words chroma, for color, and graphy, for writing. So it literally means color writing. But how on earth did a separation technique get a name like that? Well, for that story, we gotta hop back to the early 1900s. We're gonna meet a Russian botanist who was really just trying to figure out what made plants green. So this botanist, Mikhail Tswet, he took a simple glass tube and packed it with what was basically just chalk powder. Then he poured some ground up plant extract on top and washed it all down with a solvent. And as that liquid trickled down the tube, something totally amazing happened. That single green smudge of plant gunk started to separate into these distinct, beautiful colored bands. You had yellows, oranges, different greens. He was literally watching colors write themselves down the tube. And just like that, chromatography was born. Okay, so how does this magic actually work? Well, the absolute best way to think about chromatography is to imagine it's a race, a component race, where every single molecule in that mixture is a runner. And every race needs two things, right? First, you need the racetrack. Scientists call this the stationary phase. This is the stuff that stays put, like the chalk powder in Sweat's tube. And then you've got the current. This is the mobile phase. This is the liquid or the gas that's going to flow through the track and carry all the racers along with it. So here's how the race goes down. First, you get all your racers, all the different molecules lined up at the starting line. Then the race begins. The mobile phase, our current, starts to flow. And here is the absolute key. Not all racers run at the same speed. Some of them are really attracted to the racetrack itself. They like to stick to it. Others, they don't care about the track. They'd much rather just go with the flow in the current. So the ones that flow easily, they move fast and pull ahead. The sticky ones, they get left behind. And over time, that difference in speed creates this perfect separation, letting them cross the finish line one by one, all sorted out. So yeah, it really all boils down to just two things. How much a component likes to stick to the track, that's its affinity, and how much it likes to flow with the current, that's its solubility. And by picking just the right track and the right current, scientists can separate almost anything you can think of. Now, this whole balance between sticking and flowing, it isn't just a neat idea. It's actually something scientists can measure and predict. And of course, they use a simple but really powerful formula to do it. It's called the distribution coefficient, or just KD for short, but really, you can just think of it as the official stickiness factor. It's a ratio that tells you at any given moment how much of a substance is stuck on the stationary phase compared to how much is just dissolved and moving along in the mobile phase. And the rule here is super simple. A high KD means high stickiness, so that component is going to be a slow runner in our race. A low KD means it prefers to flow, making it a really fast runner. By knowing these KD values, chemists can perfectly predict exactly how a separation is going to turn out. Okay, so we have this incredibly precise way to separate things. Awesome. But what do we actually do with it? Why should any of this matter to you and me? Well, chromatography is used for two main goals. The first is analytical. That's where you use a teeny tiny sample just to see what's in it and how much. So think about testing for trace amounts of pesticides in our water. The second is called preparative, and that's where you use really large batches to purify a substance so you can use it later, like, say, removing impurities from life-saving medicines. And the technique is just incredibly versatile. By just swapping out the track and the current, you can create all these different types of chromatography for different jobs. You can use something as simple as paper or special gels like silica, or you can even use an inert gas as the current. Each one is designed to perfectly separate a very specific kind of molecule. So when you kind of step back and look at the big picture, you realize this technique is, well, it's absolutely everywhere. It's what ensures the medicine you take is pure. It keeps your drinking water safe by finding those tiny pollutants. It's used in forensics to analyze crime scene evidence and in the food industry to make sure quality is high. I mean, from purifying insulin to separating gasoline, chromatography is truly one of the invisible engines of our modern lives. And we're talking thousands upon thousands of these separations happening every single day all around the globe. It's a technique that works on scales from almost nothing all the way up to huge industrial batches, all of it working to unscramble the world so we can understand it, use it, and keep ourselves safe. So the next time you see a medicine or a clean glass of water or even a lab report, maybe you'll think of that simple color writing experiment from all those years ago. It's just a great reminder of the elegant and often invisible science that holds up so much of our world. And it really makes you wonder, right? What else is out there hiding in plain sight?